Most of the liquid solutions, usually aqueous, which we're going to discuss in our studies, are ionic solutions. There are other types of solutions, usually organic solutions, that consist mostly of undissociated neutral molecules as a solute. Therefore, now we have to acquaint ourselves with the properties of ionic solutions, and especially properties that distinguish between ideal and real ionic solutions, the ionic solutions that we're going to talk about. The theory that deals with these types of solutions, ionic solutions, is the so-called theory of electrolytic dissociation proposed by Arrhenius. The theory of electrolytic dissociation is based on three main premises. According to the first, there are some substances, so-called electrolytes, which upon dissolution, for instance in water, split into oppositely charged particles, ions. According to their nature, the electrolytes can be binary, tertiary, and quaternary. The binary electrolytes can be univalent, such as sodium chloride, or bivalent, such as zinc sulfate, when both ions are of second valency. Tertiary electrolytes can be unibivalent, such as sodium sulfate, or biunivalent, such as calcium chloride. While quaternary electrolytes can be unitrivalent, such as potassium phosphate, or triunivalent, as in the case of aluminum nitrate. According to the second premise of the theory of electrolytic dissociation, the theory assumes, in some cases incorrectly, as we will see later, that not all molecules of the electrolyte dissociate into particles, into ions. Thus, degree of dissociation, denoted by alpha, is defined, which is equal to the ratio of the number of dissociated molecules over the total number of molecules, dissociated and undissociated. According to the theory, the value of alpha depends on the nature and the concentration of the electrolytes. And so we speak of weak electrolytes when alpha is much smaller than unity, or strong electrolytes when alpha is close to unity, but never 1. The degree of electrolytic dissociation, alpha, is considered as one of the basic quantitative characteristics of the electrolytic solutions. The theory explains the changes that occur in these solutions when changing the concentration, with changing of the value of alpha during the change of the concentration of these solutions. Another quantitative characteristics of the electrolytic solutions, according to the theory, is the equilibrium constant of dissociation, which for a binary electrolyte AB has the following form. According to the theory, the value of Kc, unlike alpha, is not expected to change with concentration. For the purposes of our discussion, we will note that the degree of electrolytic dissociation is equal to the ratio of the molar conductivity lambda over the molar conductivity of the solution at infinite dilution. These quantities will be defined in another lecture. Also, if we have a binary 1,1 electrolyte AB in solution at equilibrium, then the expression of the equilibrium constant can acquire this form, where alpha is the degree of this dissociation of the electrolyte, n is the total number of moles of AB, and V is the volume of the solution. And obviously, we can cancel out these quantities. And we obtain the following expression, which obviously, because n over V is the concentration, can be written as concentration times alpha squared over 1 minus alpha. The theory of electrolytic dissociation implies also that the ions produced by the electrolytic dissociation of electrolytes behave as a system of ideal gas. In other words, they don't interact among themselves. This we may take as the third premise of the theory of electrolytic dissociation. The theory of electrolytic dissociation helped explain the existence of the so-called isotonic factor in the expression for the osmotic pressure pi, where I is the isotonic factor, C is the concentration, R is the gas constant, and T is the absolute temperature. Indeed, in some instances, that is, when electrolytes are the solute in a solution, the number of particles actually produced existing in the solution will exceed the number of particles that are expected due to the mere dissolution of the substance. And so, if μ is the total number of particles of ions that potentially can be produced by 1 mole of a substance, then alpha μ, where alpha is the degree of dissociation, will be the number of particles that are actually produced due to the dissociation, while 1 minus alpha will be the number of the undissociated molecules. And then we may express alpha as I minus 1 over μ minus 1. In this way, we have an expression for this empirical isotonic factor, which turns out to be the actual number of particles existing in a solution. Conversely, if we can find experimentally the value of this isotonic factor for a molecule that we know splits into μ number of ions, we can calculate the degree of dissociation of this electrolyte. The theory of electrolytic dissociation explains also the experimental fact that the heats of neutralization of strong acids with strong bases have practically the same value, despite the fact that completely different salts are obtained during these neutralizations. This is explained by the fact that only the reaction between protons and hydroxide ions to water takes place during these neutralizations. The rest of the ions exist only as the so-called spectator ions. They do not react among themselves and therefore do not contribute to the heat effect of the reaction. Similar is the explanation as to why, when mixing solutions of potassium chloride and sodium sulfate, practically no heat effect is observed. This is because these electrolytes are split into ions that coexist in the solution without reacting among themselves, and therefore producing no heat effect. There are some other applications of the theory of electrolytic dissociation concerning pH, buffer solutions, and so on, which we discussed elsewhere. Unfortunately, the theory of electrolytic dissociation, as formulated by Arrhenius, was found to be at odds with some experimental facts, especially concerning the strong electrolytes. Thus, it led for the search of methods to improve our picture of electrolytic solutions. Here are some examples that the theory of electrolytic dissociation is not in harmony with. For instance, the value of the equilibrium constant, Kc, obtained from the already discussed expression C alpha squared over 1 minus alpha, where alpha is the degree of dissociation, for strong electrolytes varies significantly with concentration. Also, absorption spectra of solutions of strong electrolytes indicate that these electrolytes are fully ionized. However, it is experimentally found that the molar conductivity of such electrolytes decreases with the increase in concentration. This, of course, cannot be explained with the change of the degree of dissociation alpha. Also, some small but measurable differences should be expected in the heats of neutralization, even in the case of strong electrolytes. because, according to the Arrhenius' theory, the different electrolytes are characterized by different degree of dissociation, alpha. In other words, some electrolytes will have greater heat of dissociation that would add up to the heat of neutralization. However, no such differences in the heat of neutralization are observed experimentally. Another problem that was detected was in connection with the fact that the value of alpha for a given electrolyte at given conditions at equilibrium has to be the same no matter what method for its determination is applied. However, for strong electrolytes, the value of alpha determined by conductivity measurements is close to the value of alpha obtained via osmotic pressure measurements only for very low concentration of the electrolyte. When the concentration of the electrolyte increased, it was found that the discrepancy between the values obtained by these two methods becomes unacceptable. Further, it is established that for concentrated solutions of strong electrolytes, especially of higher valency, the experimental value of alpha may exceed unity. This is unacceptable according to the Arrhenius theory, because in such a case, the molecules must split into more particles than the particles they are made of. One of the problems of the theory of electrolytic dissociation is that it does not discuss the reasons for splitting of electrolytes into ions. The main deficiency of the theory of electrolytic dissociation is its failure to recognize the existence of interactions between the ions that are formed in the solution, primarily of electrostatic nature, as well as between the ions and the molecules of the solvent. Namely, these interactions are the reasons for the discrepancies observed between the real solutions, the properties of the real solutions, and the properties that are expected provided the solutions behaved as ideal ones. We already mentioned some of the deviations from ideality of the real solutions, such as the lack of constancy of the equilibrium constant when analytical concentrations of the species are used, or the peculiar values of the degree of dissociation which do not conform with the physical meaning implied by the theory, and so on. Basically, there may be two routes to account for the deviations of the real ionic solutions from ideal behavior. Along one of the routes, one may abandon the equations derived based on expectations for ideal behavior and derive new equations, usually of more complex form, that take into account the interactions between particles in real solutions. The second approach, and this is the approach usually preferred in most cases, we will apply this approach here as well, is to preserve the form of the equations derived for ideal solutions, but to multiply the quantities participating in these equations by factors, usually empirical, that account for the deviations from ideality. This, if we want to write the rigorous form of the equilibrium constant, for instance for the ionization of a weak acid, we may use the well-known form for the equilibrium constant. However, we have to substitute the molarities in this expression with the so-called activities of the ions and the molecules. And this we write Ka equals to activity of the protons times the activity of the anions over the activity of the unionized molecules. The difference between activity and concentration, for instance of a proton, is that in the activity it is accounted for the forces of interaction between the particles in the solution. And accounting is done by multiplying the concentration by a factor called activity coefficient. Now, the forces that act between particles are independent of the nature of the particles or the concentration of these particles. But this factor, the activity coefficient, depends on the nature of the particles, on their charge, on temperature, on concentration, and so on. Because there are several ways of expressing concentrations there are several different types of activity coefficients corresponding to the concentration units used. Usually by convention, when the concentration is expressed in molarity as here, the activity coefficient is denoted by Y. If mole fraction is used as a unit of concentration, then the letter for the activity coefficient is F, while activity coefficient is denoted by gamma if the concentration is expressed in molality. We will not discuss these differences further, but we'll note that no matter how the activity coefficient is expressed, at infinite dilution, its value tends towards unity. In other words, the infinitely diluted solution already behaves as an ideal one, because the interactions between the particles of the solutions cease to exist. In this way, the equilibrium constant, which we wrote for the ionization of a weak acid, in which activity is substituted for molarities, will have a constant value for all concentrations of the electrolyte. Now, of course, here we can substitute the activities by the product of molarities and the activity coefficients of the corresponding species. Then we can rearrange this expression. And now we see that the first multiplier is the known expression for Kc. It should be noted that activities, respectively activity coefficients of the individual ions in the solution, cannot be determined experimentally. Therefore, the so-called mean activity, respectively mean activity coefficients, are introduced, which are the geometric mean of the activities, respectively activity coefficients of the ions. This is the expression for the mean activity of an electrolyte that can split into Ni plus positive ions and Ni minus negative ions. And this is the expression of the mean activity coefficient of the same electrolyte. Therefore, for a 1-1 binary electrolyte, such as the weak acid we're observing, the expression for the mean activity has the following form. Respectively, this is the form of the mean activity coefficient of a 1-1 binary electrolyte. Therefore, the numerator in this expression has to be presented in terms of the mean activity coefficient and now we can take the logarithm of both sides of this equality. Then we can multiply by -1 both sides of this equality. And using the p function, we can express this equality as follows. And because in moderately concentrated solutions, the activity coefficients of undissociated molecules are close to unity, this term is equal to 0. Finally, we have it is obvious from the discussion so far that to obtain the activities of the ions, one has to know the activity coefficients. Activity coefficients are determined by comparing the analytical concentrations of the ions with the concentrations that have to be used so that the equations of the ionic solutions conform with the experimental results. Activity coefficients characterize the electrolytic solutions at equilibrium. Therefore, equilibrium experimental methods have to be applied for their determination. And of course, the different experimental methods have to yield the same values of the activity coefficients. These methods may involve measurement of the freezing point depression, boiling point elevation, osmotic pressure, electromotive force of a galvanic cell, and so on. If non-equilibrium methods are applied, such as methods involving the measurement of conductivity or diffusion, then correction factors have to be used that account for the non-equilibrium effects appearing during these measurements. Later in this lecture, we're going to discuss in some detail some experimental methods for the determination of activity coefficients. This figure gives an idea for the experimentally found variation of the activity coefficient with concentration. In fact, logarithm of the activity coefficient as a function of square root of concentration is presented here. And this can be seen in all cases as the concentration of the electrolyte approaches zero, the value of the activity coefficient tends towards unity, or the logarithm of the activity coefficient becomes zero. This is because at infinite dilution there are practically no long-range interactions between ions. However, as the concentration increases, this causes the value of the activity coefficient to decrease and to become smaller and smaller than unity until a minimum is reached at a concentration typical for a given electrolyte. Then upon further increase of the concentration, the value of the activity coefficient begins to increase again, and in some instances it may reach values greater than unity. This behavior can be explained by considering that during the increase of the concentration of the electrolyte, the ions get closer and closer to each other, and the long-range interactions between them become more pronounced. At a certain point during this increase in concentration, the ions may get so close to each other that the forces of repulsion start to act. These forces of repulsion partially compensate the forces of attraction, and as the concentration increases, this compensation may become full at a value of the concentration typical for a given electrolyte. When these forces of attraction compensate the forces of repulsion, the value of the activity coefficient becomes again unity. Upon further increase in the concentration of the electrolyte, the value of the activity coefficient may even exceed unity. A number of empirical observations has revealed that at low concentrations of the electrolytes, the values of the mean activity coefficients do not depend on the nature of the ions present in the electrolyte, but depend only on their valencies. Thus, for instance, for solutions of 1,1 binary electrolytes, such as solutions of hydrogen chloride or sodium chloride or potassium nitrate, at low concentrations, the activity coefficients of these ions, the mean activity coefficients, have practically the same values. Notice how much different is the value of the mean activity coefficient, even at low concentrations, when there are ions of higher valencies present in the solution. It has also been found that the value of the mean activity coefficient of the electrolyte depends on the presence of all ions in the solution, on their valencies, their concentrations, and again, this value of the mean activity coefficient does not depend on the nature of these ions. Thus, to characterize the ionic solution, a quantity called ionic strength is defined, which has the following form, where Ci is the concentration of the ions of a given type, and Z is the valency of these ions. Obviously, for 1,1 electrolytes, the value of the ionic strength coincides with the value of the concentration, while for the rest of the electrolytes, the ionic strength is greater than the concentration. Also, it has been established empirically that the mean activity coefficient depends on the ionic strength in the following way. Where B is an empirical constant. Later in this lecture we will derive this expression considering the electrostatic forces that act between the ions.